Welcome to Chapter 10, where we begin our study of sequences and infinite series. In this first section, we're going to do an overview of these. This chapter covers topics that lie at the foundation of calculus, indeed at the very foundation of mathematics. And our first task is to make a clear distinction between a sequence and an infinite series. A sequence is an ordered list of numbers, for example, 1, 2, 3, 4, etc., while an infinite series is a sum of numbers, 1 plus 2 plus 3 plus 4, etc. The idea of convergence to a limit is important for both sequences and series, but convergence is analyzed differently in the two cases. To determine limits of sequence, we're going to use the same tools that we've used before, specifically to find limits of functions at infinity. The analysis of infinite series requires new methods, which are going to be introduced in this chapter. Consider the following list of numbers: 1, 4, 7, 10, 13, etc., which means ongoing. We can see by the relationship between the numbers that each subsequent number in the sequence is 3 greater than the one before it. 1 plus 3 is 4, 4 plus 3 is 7, 7 plus 3 is 10, etc. Okay? With this rule, we could extend the list indefinitely. This is a sequence where each number in the sequence is called a term of the sequence. We denote sequence in any of the following forms: as a list, a sub 1, a sub 2, a sub 3, a sub n, etc., much like we did. That first one is just listing all the members. Or we can denote it with kind of an idea that each member is a sub n, where n equals 1 and goes up to n equals infinity. This is the middle one there. So let's look at that same list of numbers, that same sequence we were looking at: 1, 4, 7, 10, 13, etc. A recurrence relation, also known as an implicit formula, gives the first term and a general rule for finding for the next term. So we can see in here that our first term is equal to 1, and to find our next term, we're going to add 3 to that previous term. So here we would say the recurrence relation is that a sub 1 equals 1, and a sub n plus 1 equals the previous term, a sub n, plus 3. So if we were trying to find a sub 2, right, this is 1 plus 1, so this would be a sub 1 plus 3. If we wanted to find a sub 3, this is 2 plus 1, so n is 2. We get a to the second member, which is 4, plus 3, which is 7, etc. Okay, this is a recurrence relation, which again gives us the first term explicitly and then gives us an implicit formula so that we have to find each term. So in this case, if we wanted to find the sixth term, we'd have to keep going through and building each of the terms until we came up with the fifth term, from which we could then calculate the sixth term. An explicit formula allows us to determine any term from the value of n. So we know that a sub 1 equals 1 plus 3 times 0, right? We know that a sub 2 equals 1 plus 3 times 1. We know a sub 3 equals 1 plus 3 times 2. Again, if you're looking at the subscript and thinking that is n, look at the formulas and see if you can figure out the pattern or the formula based on n for a sub n. Well, here n is 1, so you could think that maybe this is it, n plus 3 times 0, but that doesn't work here because n is 2, so this can't be the n. And 3 is constant in both of these. So 1 and 3 are constant in all of these formulas, but the number that's changing is this number, 0. Think about its relationship with n. The number that's changing is this one. It's 1 when n is 2, and it's 2 when n is 3. So if we think about a formula for a sub n, we get 1 plus 3 times n minus 1. If n is 2, then this number is n minus 1. If n is 3, this is n minus 1. So we get a sub n equals 1 plus 3 times n minus 1. Again, when n is 1, n minus 1 is 0. When n is 2, n minus 1 is 1. When n is 3, n minus 1 is 2. So a lot of times with sequences, we're trying to figure out how to create this explicit formula so that we can find any member. Here all we've done is distribute the 3, so we get 1 plus 3n minus 3, which simplifies to 3n minus 2. With an explicit formula, this allows us to find any member, like the 147th member, which if we use the recurrence relation, would take us a long time because we'd have to go all the way up to 146 to find the measure, excuse me, the value for 147, whereas here we can do it quite easily from our formula 3n minus 2. Since n is 147, 3 times 147, we calculate that minus 2 and we get 439. This leads us to the definition for sequence. A sequence a sub n is an ordered list of numbers of the form a sub 1, a sub 2, a sub 3, a sub n, ongoing. A sequence may be generated by a recurrence relation of the form a sub n plus 1 equals a function of a sub n for n equals 1, 2, 3, etc., where a sub 1 is given. A sequence may also be defined with an explicit formula of the form a sub n is a function of that subscript or index n for n equals 1, 2, 3, etc. So let's look at example 1, explicit formulas. Example 1, use the explicit formula for a sub n from n equals 1 to infinity to write the first 4 terms of each sequence. Sketch a graph of the sequence. Part a sub n equals 1 over 2n, 2 to the power of n. So this is pretty straightforward to calculate the first 4 terms and then just simply sketch a graph. Now when you're doing the graph, the n value will be the x-axis, and the a sub n, your formula value, will be the y-axis. So go ahead and hit pause, do this. This is pretty straightforward and simple, and then you can compare your results. So substituting n equals 1, 2, 3, 4 into the explicit formula, a sub n equals 1 over 2n, we get 1 over 2 to the 1, 1 over 2 to the 2, 1 over 2 cubed, 1 over 2 to the 4th. When we calculate those out, we get 1/2, 1/4, 1/8, 1/16. Pretty straightforward. When we graph those on a calculator, when we graph those on the graph, we can see here's a sub 1 is 1/2, and then 1/4, and then 1/8, and then 1/16. What's happening is we can see that this is actually converging on a sub n equaling 0. So this is actually converging to the x-axis or to the value of a sub n equals 0. So these values are getting smaller and smaller and smaller. So as n goes to infinity, the value of this function a sub n goes to 0. There's also a part B in your text. I suggest that you can look through that. I'm not going to do that. It's a little bit more calculated, a little more complicated explicit formula, but it's not that big a deal. And it'd be interesting for you to try that and see what happens with the graph. Okay, so go into your text, look at example 1b. Both the solution and the graph are given to you there. So now let's try example 2. Recurrence relations. Use the recurrence relationship for a sub n to write the first 4 terms of the sequences a sub n plus 1 equals 2 times a sub n plus 1, where a sub 1 equals 1, and a separate sequence a sub n plus 1 equals 2 times a sub n plus 1, where a sub 1 in this case equals -1. So go ahead and hit pause. Notice you're going to be calculating 2 sequences. So you're going to have 4 terms for the a sub n plus 1 on the left and the a sub n plus 1 on the right. Hit pause and then try these. Once you're ready, hit play again and come back. So when we start with 1, notice that what we get by plugging in the values, a sub 1 is 1, so we get for a sub 2, this is 2 times a sub 1, 1 less, plus 1, which gives us 3. A sub 3 equals 2 a sub 2 plus 1, which gives us 7. A sub 4 equals 2 times a sub 3, this is 1 less, plus 1, which gives us 15. And so we can see when a sub 1 is 1, we have a series that's not converging, it's just expanding continuously. So this would keep going on to infinity. So this does not converge at all. However, when we start with a sub 1 being negative 1, notice what happens. Here we get a sub 2 equals 2 times a sub 1 plus 1. Well, that's 2 times negative 1 plus 1, which gives us negative 1. Well, each one that we're doing is going to use the same previous value, so all of these are then going to be negative 1. So here we have it's a constant for the whole thing, so it does converge at negative 1 throughout the entire sequence. So this is a really interesting example because notice we have the same relationship, we just have a different starting point, and that creates a totally different sequence when we look at it over the infinity, and also trying to figure out what's happening with conversion. So this is a good observation point that the starting point really does matter. So now let's try example 3, where you get to do all kinds of things. Here you're going to find a couple more terms. Then you're going to find the recurrence relation. And then in part 3, you're going to find an explicit formula for the nth term. So see if you can do this. Hit pause and try this, and then try to find those 3 answers, okay? Get as far as you can, and then hit play and continue on. Again, hit pause, try these 3 problems with this sequence, and see if you can solve it. All right. Well, we can see that for part A, negative 2 plus 7 is 5, plus 7 is 12, plus 7 is 19. So part 1 is actually pretty easy. We just have to add 7 to 19 and then 7 again. So we get the next 2 terms that are 26 and then, of course, 33. Now we have to find a recurrence relationship that generates the sequence. Well, remember recurrence relationship, we identify the first value, which is a sub 1, which is here, which is negative 2. And then we have to figure out what's going on. So we know that a sub n plus 1 equals the previous member, which is a sub n, and then plus the 7 as we saw in this. So that one's actually pretty straightforward too. Here we have a different initial starting point because a sub 0, or the first term, is actually negative 2. Okay. Now we have to kind of look at, several of those first terms, and it helps if you look at them like we did before, figuring out what, a sub 1 is, a sub 2 is, etc. Now here they start with n equals 0, okay? So let's do that. So you get a sub 0 equals negative 2, right? A sub 1 would equal negative 2 plus 1 times 7. And a sub 2, this was sub 2, would equal negative 2 plus 2 times 7, right? So we get a sub 0, a sub 1, a sub 2. When we see the pattern there, then you can get that a sub n, here we are, here's the formula, a sub n equals a sub 0 plus 1 times 7. So if we're trying to find n, we again notice that what's changing is the number inside the parentheses, the multiplier. So when n is 1, we have 1 times 7. When n is 2, we have 2 times 7. So notice that the n is matching up. So we actually have negative 2 plus n times 7, or that simplifies to 7n minus 2. And of course, when n is 0, 7 times 0 is 0 minus 2, which gives us the first member. So these take a little bit of work, and you have to kind of look for the pattern, trying to figure out what's changing in here and what's staying the same. What's changing will be the value of n for each term, and then trying to see how it relates. There is a part B in this problem, and I suggest that you go into the text and try part B, as you've seen how to do this one here. So let's look at the definition of the limit of a sequence. This should seem somewhat familiar to you from Calculus 1, specifically the limit as x approaches infinity, or the limits at infinity. If the term of a sequence, a sub n, approach a unique number L as n increases, that is, if a sub n can be made arbitrarily close to L by taking n sufficiently large, then we say that the limit as n goes to infinity of a sub n equals L exists, and the sequence converges to L. If the terms of the sequence do not approach a single number as n increases, the sequence has no limit and the sequence diverges. This is the idea that we had before, and what's happening is as we go to the outer edges of a graph, what's happening is that we're getting a horizontal asymptote, and that is that the graph as we go to infinity or negative infinity is leveling out into a horizontal line. So if we get a horizontal kind of line, then we have a convergence at that value of L, or a horizontal asymptote at that value of L. And if it doesn't converge to any specific horizontal value, y value of L, then we say that the sequence diverges. So let's look at some examples of these. We have 3 different examples here, A, B, and C. What you're asked to do here is to write the first 4 terms of each sequence. If you believe the sequence converges, make a conjecture about its limit, like it's saying where does it converge to, what is the value of L, and if the sequence appears to diverge, explain why. Okay, so I've got the pause up there, so why don't you hit pause and try this. Just find the first 4 terms and see what you think, and then once you're ready, hit play again. And there's 3 different screens here for A, B, and C, so you can do one at a time if you wish, however you want to do it. So let's look at A, negative 1 to the power of n, all over n squared plus 1 as n goes from 1 to infinity. So let's find the first 4 terms. When we do this, it's worked out here for you. We get negative 1/2, 1/5, negative 1/10, 1/17. So if I just looked at these 4 answers, what do you think's happening, convergence or divergence? By looking at those numbers, because it's oscillating between positives and negatives, I might think that it is diverging, because it doesn't seem like it's heading to any specific value of L. And so sometimes this limited number might give us the wrong intuition or idea about what's happening, inference. Okay, but do notice that what's happening as we go from negative 1/2 to negative 1/10, that it's shrinking. And the same thing from 1/5 to 1/17, it's shrinking. If we look at the graph, here it becomes a little bit more obvious that instead of instead of diverging, it's actually converging around the value of 0. So here we would say that this is this is a converging sequence, and its limit is 0. It's converging to 0, to the y value of 0. The limit is 0. So now let's look at B again. Hit pause and then find your first 4 values and see what you think here. Well, when we do the first 4 values, we get negative 1, 1, negative 1, 1. Here we're just going through the x-axis, if you will, the quadrantal 180 and 360. So we're just going to keep oscillating back and forth between 1 and negative 1. This is pretty straightforward that this is not oscillating. I mean, it's not converging, but it is indeed diverging, and you can see that because it doesn't go to any one value. Now you might think, well, wait, it's going to two values, 1 and negative 1, but there's not one consistent value as we go to infinity, so this is divergent. So we're about halfway through the lecture now. It's about a 40-minute lecture. So this is a good time to take a break, get a drink, take a walk, ponder the picture I have there and the saying from Joseph Campbell, one of my favorite. The big question is whether you're going to be able to say a hearty yes to your adventure. So take a break. When you're ready, come back, refreshed, get a coffee, get a drink, and then start up again. So now let's look at our last example, C, where we have negative 2a to the n, and a sub 1 equals 1. Again, hit pause, find the first four members, and then see if you think it's converging or diverging. So here we get 1, negative 2, 4, negative 8. Again, we have an oscillating feature here, but we can see that even with just these four members, that it's getting larger. And so what's happening, if we look at the graph, we can see that it's actually kind of expanding out. It's not leveling out, which is convergent, it's expanding out, so it's divergent, and it just diverges, so there's no limit here. Okay? Now, what I want you to notice too about this example is that both A and B problems were explicit formulas, where in C, this was the relative, the reoccurrence relation, excuse me. So you can do them in either way, and you've done, in this example, we've done them in both explicit formulas and the recurrence relation. We could easily find the four members and then figure out what's happening. So let's look at our next example. Example 5, another limit of a sequence. Enumerate and graph the terms of the following sequence and make a conjecture about its limits. A sub n equals 4n to the power of 3 over the quantity of n cubed plus 1 for n equals 1, 2, 3. Again, we have an explicit formula here. Hit pause, plug in some values, and see if you can decide whether this is a convergent sequence, and if it is, what is its limit? What is it converging to? What y value? Or is it divergent, which it doesn't level out to any specific y value. If we look at these table of values, these are the first 14 members of this sequence. We can see that it's getting closer and closer to 4. If we graph it, it's quite obvious that this is a convergent sequence and approaches 4 as n goes to infinity, so the limit of this sequence is 4. Let's look at our next example, 6, a bouncing ball. A basketball tossed straight up in the air reaches a high point and falls to the floor. Each time the ball bounces on the floor, it rebounds to 0.8 of its previous height. Let h sub n be the high point after the nth bounce, with the initial height being h sub 0 equals 20 feet. Find a recurrence relation and an explicit formula for the sequence, part A. Part B, what is the high point after the 10th bounce, after the 20th bounce? And part C, speculate on the limit of the sequence, h sub n. Hopefully, just conceptually, you know the answer to C, or have an idea about what you think it would be. But again, hit pause and start working through this problem, identifying the recurrence relation and then an explicit formula based upon the data given. Okay, so hit pause, and then when you're ready, continue on. So for the recurrence relationship, we want to look at what's happening with each one, right? So we have h sub 0 is 20, h sub 1 is 0.8, h sub 0 are 16 feet. Notice that h sub 2 is 0.8, h sub 1. Well, h sub 1 is 0.8, h sub 0, so we get 0.8 squared h sub 0. When we can identify now what's happening here, again, what's changing as we change the value of n, which is what's really important in the recurrence relation. And so we can see here that h sub n plus 1, the next one, equals 0.8 h sub n with the initial, with the initial member being 20 or 20 feet. And this is pretty straightforward given to it. And you may not even need to, walk through those steps. It even tells you that it's 0.8 of the previous height. So this is a pretty straightforward recurrence relation. Here's also a good diagram of the bounce. If you haven't finished B and C, go ahead and work on that. Oh wait, I'm sorry. I still need to give you the explicit formula for this. Okay. To find the explicit formula, note again that what's happening with each level of n, so as I pointed out in the last slide, so h sub 1 is h sub 0 0.08, h sub 2 is h sub 0 times 0.08 squared, h sub 3 is h sub 0 0.8 cubed, etc. So we know that h sub n is equal to h sub 0 times 0.8 to the n, because each value is the exponent, each value of n is the exponent on 0.8, and of course h sub 0 equals 20, so we get this formula, 20 times 0.8 to the nth power. Okay, again, what you're trying to do here is see what's happening, what's changing in here, what's relative to the value of n in here, so that we can write an explicit formula in terms of this starting point. So B is rather easy to calculate now that we have both a recurrence relation, which we could go through and calculate all 10 or all 20, but of course we don't want to do that. Once we have the explicit formula, then it becomes really simple to find a specific value that's higher up without calculating all the previous values. So here we can see that h sub 10 is going to be 20 times 0.8 to the 10th power, which is 2.15 feet. Doing the same thing with the height after the 20th bounce, h sub 20 equals 20 times 0.8 to the 20th power, or 0.23 feet. So this is pretty straightforward once you've identified the explicit formula. And the last part is C. Well, what would you expect to happen with a bouncing ball? That eventually it's going to stop bouncing, so the height is going to be 0. And we can even see that by looking at the value at 10 and the value at 20. And here you have a graph that's showing what's happening after each bounce. But again, this is quite intuitive that this is exactly what we'd expect. And there's some similar exercises in the text between 57 and 60 that you might want to try, especially preparing, identifying the relation and the explicit formulas for these. So now let's switch over to the concept of infinite series. And remember that an infinite series is viewed as a sum of an infinite set of numbers. It has the form a sub 1 plus a sub 2 dot 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 plus a sub n continuing on, where the terms of the series a sub 1, a sub 2 are real numbers. This brings to mind a pretty obvious question, that if we're adding up an infinite group of numbers, a set of numbers, a sequence of numbers that never ends, how could that ever possibly, how could that sum ever possibly equal a finite number? Why wouldn't it just be, infinite all the time? Okay. Well, let's look at an example, and this is a pretty standard example in calculus for this type of explanation. On the right here, you see a square, a unit square with sides equaling 1. So the area of the square is 1. But let's subdivide that square, as we see here in the top picture, and we let S sub n be the area of the colored region in the nth figure. The area of S sub 1 is 1/2 of the area of the square, or 1/2. Now, S sub 2, the area of the colored region in the second figure, is 1/2 that we had S sub 1 plus the next member, which is 1/2 of what's left. So we get 1/2 plus 1/4, that's the area of this little blue square, which gives us 3/4. Now the challenge here, and then if we did it again, then we'd have S sub 3 equals the 1/2 plus the 1/4, and then of course half of 1/4 is 1/8, which we see here. Now the challenge here is to move from this kind of visual to figuring out a formula or an expression for the sequence, the series. And so we have 2 to the 1 minus 1 over 2 to the power of 1 for S sub 1. For S sub 2, we have 2 squared minus 1 over 2 to the power of 2. And for S3, we have 2 to the power of 3 minus 1 over 2 to the third power. Okay, I think you might be able to see what's happening here and figure out what the ultimate end is going to be, or the sum for this infinite series. Okay, if we keep adding those values, we can see that what we're doing is we're just chopping the unadded area in half, and so this is getting smaller and smaller and smaller infinitely until we've basically come as close as possible to filling up the square, which of course has an area of 1. The explicit formula that we saw the pattern arriving is that S sub n equals 2 to the power of n minus 1 over 2 to the n. This can be analyzed to verify our assertion that the limit as n goes to infinity of S sub n equals 1, and we will do that in the next section. So again, this example is just to show you that what can happen, it is possible to add up an infinite sequence of numbers and have them equal a finite number. Okay? Let's look at another example, number 7, working with series. Consider the infinite series 0.9 plus 0.09 plus 0.009 plus 0.0009, where each term of the sum is 1/10 of the previous term. Part A, find the sum of the first 2, 3, and 4 terms of the series. B, what value would you assign to the infinite series 0.9 plus 0.09 plus 0.009 plus ... Again, this is pretty straightforward. So hit pause and calculate A and B. Hit pause now. So if the first member is 9, if I sum the first 2 members, I get 0.99. The first 3, I get 0.999. And of course, if I sum all 4, I get 0.9999. Pretty straightforward, since each time the 9 is moving over 1 decimal place. Well, based upon what I'm seeing here, it's pretty straightforward what would we assign to the sum of the infinite series, or what would we assign to the value of the infinite series, which of course is the sum of all the members. Well, this is going to be 1, right? You can see that each time we're getting closer and closer to 1, so we're just, these 9s are going to go on forever in an infinite series, and so the value would be 1. Next, we're going to look at how do we take this and make a formula from it, and how does that help us kind of work through some more of the infinite series. So when we look at the example from, when we look at the series from example 7, we can see that the member S sub n, these were all the terms that we were given, is equal to the summation of all the terms from the first term to the nth term of 9, which was the first term, times 0.1k, because each term is 1/10 of the previous term, and if we start with 9, then we actually have the k value of 1 here, and that creates the first term, which would be 0.9. Okay? We also saw that if we applied the limit as n went to infinity, if we just kept adding and adding and adding, we knew that this limit would equal 1. So we can apply the limit to s sub n as n goes to infinity, which is what we did conceptually. And then when we substitute in how to calculate the nth term, which we do here, and what we have now is a new object. And this is the infinite series. The infinite series and its value is the limit of the sequence of partial sums. Okay? So this infinite series, which by definition is a sum, is again the limit of the sequence of partial sums. Okay? This brings us to the definition of an infinite series. Given a sequence, a sub 1, a sub 2, a sub 3, etc., the sum of its terms, a sub 1 plus a sub 2 plus a sub 3, ... equals the sum from k equals 1 to infinity of a sub k. And this is called an infinite series. The sequence of partial sums, s sub n, associated with this series has the terms s sub 1 equals a sub 1, s sub 2 equals a sub 1 plus a sub 2, s sub 3 equals a sub 1 plus a sub 2 plus a sub 3, all the way down to a sub n, which is a sub 1 plus a sub 2 plus a sub 3 plus ... all the way up to a sub n, which also can be written as the summation from k equals 1 to n of a sub k, for n equals 1, 2, 3, etc. If the sequence of partial sums, s sub n, has a limit L, the infinite series converges to that limit, and we write the summation of from k equals 1 to infinity of a sub k equals the limit as n goes to infinity of the summation from k equals 1 to n of a sub k, which equals the limit as n goes to infinity of s sub n equals L. If the sequence of partial sums diverges, the infinite series also diverges. So all this is saying is if the partial sums have a limit, then that same limit applies to the value of the infinite series. Now let's look at our last example, number 8, a sequence of partial sums. Sequence of partial sums. Consider the infinite series, the summation from k equals 1 to infinity of 1 over k times k plus 1. Find the first 4 terms of the sequence of partial sums. This is really straightforward. Just start with k equals 1, then k equals 2, then k equals 3, and then k equals 4. But of course, remember when k equals 2, you also have to add the value from k equals 1 plus the value of k equals 2, and so forth. And then for part B, find an expression for s sub n and make a conjecture about the value of the series. So go ahead and hit pause and try A and B, and then when you're ready, start playing again. So here we can see that when we go from k equals 1 to k equals 2, when k equals 1 we get 1/2, when k equals 2 we get 1/6, so we add those. When k equals 3 we get 1/12, so we add all 3 of those members. And when k equals 4 we get 1/20, and we add all 4 of those members, and we get to 4/5. You can see we've gone from 1/2 to 2/3 to 3/4 to 4/5. So what would you think is going to be the value of the series? Based on the pattern in the series, a reasonable conjecture is that s sub n equals n over n plus 1 for n equals 1, 2, 3, which produces 1/2, 2/3, 3/4, etc. So looking at these values, 1 over 2, 2 over 3, 3 over 4, that's the pattern we notice. And this is, again, the tricky part, is to go from just simply plugging in numbers and calculating to actually figuring out an expression for a partial sum, okay? So this is kind of a game in a way. It's a game or a puzzle. And so this is, again, part of the challenge. So make sure you try some more of these problems in there in addition to your homework. It appears the values of S sub n approach 1 as so a reasonable conjecture that the limit as n goes to infinity equals the limit as n goes to infinity of n over n plus 1, which is the formula, which in this case does equal indeed 1. Okay? So this chapter has 3 big ideas for you to keep in mind, and it's sometimes difficult because of the notation. A sequence, and you see the set there is a sub 1, comma a sub 2, a sub n, is an ordered list of numbers. It's a list. An infinite series is the summation of a sum of numbers from k equals 1 to infinity. A1 plus A2 plus A3. And then a sequence of partial sums, S sub 1, S sub 2, S sub 3, is where S sub n equals A sub 1 plus A sub 2 all the way up to A sub n. And we use that to then evaluate the infinite series, if you will. Okay? So, you know, since series and sequence both begin with S's, it's really easy to get confused on these, and sometimes I have to sit back and remember, and then also the notation. The notation for the members or the indexes with the indexes are A, and then this, of course, is a partial sum. The S stands for sum. It doesn't stand for series or sequence. It stands for sum. Okay? This table shows the correspondence between sequence series and functions, and between summation and integration. For a sequence, the index n plays the role of the independent variable and takes on integer values. The terms of the sequence, a sub n, correspond to the independent variable. With sequences, a sub n, the idea of accumulation corresponds to summation, whereas with functions, accumulation corresponds to integration. A finite sum is analogous to integrating a function over a finite interval. An infinite series is analogous to integrating a function over an infinite interval.